So we're going to end our chapter on area and integrals kind of where we started, and that's with estimating. But we're not going to estimate in the same way, because if you think about the estimation that we did, it used those clunky rectangles. And unless we draw an infinite amount of rectangles, which usually we don't do, that rectangle method has some limitations. But I still want to talk to you about estimating because there is a place for it. And normally the place is when we don't have an equation. And so let's say we have some type of data, or maybe just some type of graph that doesn't have an equation like the one that's shown here. And we want to try to find the area of this graph from A to B. Well, of course, we know that the area is always going to be fully between the graph and the x-axis. And we can start to kind of see that area, maybe if we draw in a few more lines. And if we still subdivide, now what we're going to do is we're going to subdivide into technically into n amount of intervals. But I'm going to, it's going to look like that we're subdividing into 4 intervals. So maybe we could say that we have x sub 1, x sub 2, let me space these out a little bit better. Let's put x sub 1 right here. So we got x sub 1, we've got x sub 2, x sub 3, and x sub 4. I guess technically we could go back to the first one and call that x sub 0, could we not? And we're going to make 4 subintervals. Now, you know from our previous study that the subinterval is going to end up dividing our space that is under this curve. So I'm going to still draw those lines so we can kind of see these 4 regions. But can you think of a better shape that we could use to kind of connect the dots between these subintervals? Can you think of a better shape than a rectangle? Well, it turns out that you're right. That better shape has always been, and really should be, a trapezoid. Because if you think about it, when you connect the dots that are represented between each of these subintervals, a straight line, a diagonally straight line, is going to give us a much better estimation, a much better fit than rectangles. And so the secret's out. We're going to estimate with trapezoids. And we're going to end up in a few minutes discovering that there's a pretty nice formula that enables us to get the area under this graph using trapezoids. Let's talk about trapezoids a little bit more. First of all, it would be helpful if we knew the area of a trapezoid. And it is a formula that we've seen, but it doesn't hurt to see it again. Even I have to look at it just to make sure. It's given in different ways. Sometimes it'll be given as the sum of the bases, times the height of the trapezoid, times the height, and then it still gets divided by 2. I want to show you what the bases would be, what the sum of the bases would be for each of these trapezoids. Also want to help you see what the height is. Let's actually start with the height. You see our trapezoids are kind of like turned 90 degrees. They're kind of like moving up and down. But the height is always the perpendicular distance. And so the height is really just the length of each one of these subintervals, which, as we'll discover and remember, is going to be the same value. The bases are actually these green distances. They are actually these y values. And so, for example, in our first trapezoid here, our first y value would be the one that matches with x sub 0. Fittingly, we'll call it y sub 0. Our next y value would be y sub 1. If we work through the y sub 2, y sub 3, and either y sub n or y sub 4. I'll tell you what, I'm going to call it y sub n. I didn't realize that I wanted to do the same thing with my x sub n. That just means that I could technically go out to any amount of subintervals that I want to. So you ready to find the area of some of these trapezoids? In fact, how about of each of these trapezoids? The first one right here,
The first one right here is going to have a sum of bases represented by, let me back up a step. Let's call this the trapezoidal area approximation. Just kind of want to make sure we realize that we're now using trapezoids to approximate that area. All right, so ready to go with our first trapezoid. The first base there, the first y value is y sub 0. If we add to it the next y value, it's y sub 1. So there we've got the sum of the bases times the height, and it's always divided by 2. About the next trapezoid. The next trapezoid has as its first base, as its height is y sub 1 again. Notice that we're using y sub 1 again, and then y sub 2. The height is x, or check that, h again. How about the next one? The next one's going to be y sub 3. I'm going to go ahead and move down a line. I'm kind of running out of space here. Excuse me, it's y sub 2 plus y sub 3. That would be my next trapezoid. The height is still h, and it's still divided by 2. The reason there's going to be a formula that comes from this is you should feel like that we're kind of repeating some values. In fact, we're repeating a lot of values. But let's continue. As I get to my last trapezoid here, I want to make sure that you realize that the base is y sub 3. The other base is y sub n. So we're going to have y sub 3 plus y sub n, obviously the same height, and one more time divided by 2. Now, if you take what has been written here, you can definitely condense it. You can simplify it. You can write it more simply. First of all, every one of these fractions has an h over 2. So I'm going to factor that h over 2. I'm going to factor that out of every one of these. Now the funny thing is, all that leaves you with is a bunch of y values that are conveniently being added together. Where have you heard that before? But if I take my first set of y values, it's y sub 0 plus y sub 1. If I take my next set of y values, it's y sub 1 again, plus y sub 2. If I take my next, it's y sub 2 again, plus y sub 3. And then my last one here is y sub 3 plus y sub n. Okay, we're not done simplifying yet, because inside of the parentheses, we have some sharing going on. In fact, we have 2 y sub 1s. We have 2 y sub 2s. We have 2 y sub 3s. But we don't have 2 y sub n's or y sub 0s. The ones on the end are only used once. Well, we just made ourselves a little formula, and it's a little formula that gives us the trapezoidal approximation of an integral. Basically, using trapezoids, we're able to add all the y values. Notice that we're doubling the ones in the middle, and we're just going to multiply that by h and then divide it all by 2. We end up with the area, the approximated area under a graph. It's funny, it's h that gives kids the most trouble. And so I want to make sure that we're clear that h is the length of the interval, but to make that length consistent, we want to think about the fact that we have an overall interval between a and b. So we have this overall interval between a and b, and we just want to divide it evenly. We want to divide it by the number of subintervals. So we're going to give ourselves a little extra statement here where h is equal to the length of the interval, b minus a, divided by n. And again, that's going to give us the height of every one of those trapezoids. If you're asked to do a trapezoid approximation for an integral, you don't actually do the antiderivative. You don't actually do the integral that way. If you're asked to do a trapezoid approximation, you're going to add up all the y values, making sure that you double all the ones in the middle, and then multiply by h, divide by 2, and we have ourselves the estimated area under the curve. Notice again that we're going to use n subintervals, meaning whatever amount we want, and the height will be b minus a over n. Now next time we gather, I'll show you how to do this for an actual problem that has actual numbers. It won't be too surprising what you find out. And then we're going to get ourselves set up for a little mini project. Yeah, you guys are going to actually find the area of something in the real world. It's going to involve your car. So get your favorite car or your favorite friend's car or your dream car, and there's going to be something that there'll be an area that we find, and we'll find it using trapezoids.